Welcome to the Deep Dive, your shortcut to becoming incredibly well-informed on fascinating topics. We take a stack of sources, extract the most important nuggets, and bring you the insights you need fast. Today, we're plunging into the world of the Finite Element Method, or FEM, specifically focusing on its linear analysis for solids and structures.
Right. Our mission for this deep dive is really to unpack the fundamental principles, the procedures, and, the practical applications of FEM. It's a method that truly revolutionized engineering. Think about designing, say, a complex aircraft wing without ever building a physical prototype first, or maybe crash testing car designs virtually. It saves millions and lets you iterate ideas super fast. FEM has just significantly increased the possibilities for safe, cost-effective design, especially when you're tackling these really complex engineering problems.
And our primary source for this journey is some fantastic material from Klaus-Jürgen Bae's MIT course, Finite Element Procedures for Solids and Structures Linear Analysis. What's great about Bae's approach, I think, is his emphasis on the physical explanations, rather than just dense mathematical derivations. Plus, he focuses on techniques that are actually implemented in programs people use, like SAP, that's the structural analysis program, and ADA, automatic dynamic incremental nonlinear analysis.
Exactly. And when you're analyzing any complex engineering problem, there are really three essential stages. First, you have to select a mathematical model, something that accurately represents your physical problem. Second, you analyze that model. And third, you interpret the results. FEM plays a critical role in that middle stage, the analysis of the model itself.
Okay, so get ready to explore how engineers idealize, break down, and ultimately solve some truly complex problems. So we've talked about its power and reach, but let's truly unpack the core idea here. What is the finite element method, fundamentally? What makes it such a game changer?
Okay. At its core, FEM is this powerful mechanism, right? It takes complex, continuous systems like, imagine a huge structure where the response is theoretically described at an infinite number of points by differential equations.
Which is impossible to solve directly, usually.
Exactly. Impossible for a computer anyway. So FEM reduces them into discrete forms. This means the response is described at a finite number of points using algebraic equations, and those are solvable on digital computers. It's kind of like taking an infinitely smooth curve and approximating it with, say, a series of tiny straight-line segments.
The sheer breadth of FEM's application across so many engineering disciplines is truly striking, isn't it? I mean, we see it everywhere. Civil, aeronautical, mechanical.
Ocean, mining, nuclear.
Right. And even biomechanical engineering. The source had examples like analyzing massive cooling towers, dams.
Or the complex inflation of tires, yeah. Or even really intricate components like a spherical cover of a laser vacuum target chamber. FEM gives you crucial insights into all of these.
So what's the actual process like? How does an engineer use it?
The FEM solution process is quite systematic. You start with a real-world physical problem, naturally. Then you establish a finite element model of that physical problem. Next, you solve that model on the computer, interpret the results. And then, based on that interpretation, you might go back and revise or refine your model, maybe for greater accuracy or to look at different scenarios. It's kind of a continuous loop of refinement. And
what kinds of basic problems does FEM help us solve? Are there categories?
Yeah, broadly, FEM addresses a few basic problem types. You've got steady-state problems. It's essentially statics. The response doesn't change with time. Think of a bridge just holding a constant load.
Okay, simple enough.
Then there are propagation problems, or dynamics. Here, the response does change over time. This requires including what are called D'Alembert forces, basically. These are inertial forces. They account for the acceleration and movement of the system itself.
Right, things moving around.
Exactly. And finally, there are eigenvalue problems. These pop up often in dynamic analysis and also in buckling analysis. They're about finding a structure's natural vibration patterns, its frequencies, and maybe its critical buckling loads. Mathematically, they often look something like A times V equals lambda times B times V. Think of it like finding the unique fingerprints of how a structure inherently wants to deform or vibrate.
Could you give us a really simple example to make this concrete, like a basic building block before we get to the super complex stuff?
Absolutely. Let's consider a simple spring system. It's already a discrete system, which makes it a great illustration. We evaluate the equilibrium requirements for each individual element, each spring. Okay, then we assemble these equilibrium requirements using a technique called the direct stiffness method. This whole process ultimately forms the global equilibrium equations for the entire system, which we usually write as Ku is R.
Ah, Ku equals R. K is stiffness, U is displacement, R is the load.
Precisely. It's a bit like building with Lego blocks. You connect the individual pieces according to the rules, and suddenly you have the equilibrium equations for the whole spaceship or whatever you're building.
That KUR equation is absolutely fundamental, it seems. We've touched on it using a simple spring system. But how do we arrive at something so fundamental when we're talking about a complex, continuous structure like a bridge or a dam? That seems like a bigger leap.
It is a bigger leap, you're right. Besides that direct approach, there's also what's called the variational approach. This operates on an extremum formulation. It's quite elegant, actually. Instead of directly balancing forces on every little piece, it uses a principle from physics. Like imagine stretching a rubber band. It naturally wants to settle into the position where its stored energy is at a minimum, right?
Okay, yeah, lowest energy state.
Exactly. So this approach finds the structural equilibrium by finding that minimum energy state for the entire system. Mathematically, we define something called a total potential functional, often written as a T, pi. It represents the system's strain energy minus the total potential of the applied loads. And the beauty of this is that the equilibrium equations for the system, the KUR, are obtained by simply setting the variation of A to 0, finding where it's stationary.
So minimizing that energy function gives you the balance equations.
Precisely. And this is directly linked to a really powerful fundamental concept in mechanics called the principle of virtual displacements. In essence, it states that if a system is in balance, the total work done by all the forces for any tiny imaginary movement of virtual displacement has to be 0. It's a very elegant way to derive those equilibrium equations without having to meticulously track every single internal force.
Okay, so we have this powerful method, these fundamental equations. How do we actually build these finite elements? What's the process behind creating the building blocks themselves?
Right. So the displacement-based finite element method, which is honestly the most widely used in practice, is essentially a modern application of some classical numerical procedures. You might have heard of the Ritz method or the Galerkin method.
Vaguely, maybe from engineering classes way back.
Well, the Ritz analysis method is a good place to start. In this method, you substitute what are called trial functions into that total potential functional, PRAC. Think of these trial functions as educated mathematical guesses for how the displacement will behave within an element, like approximating a complex curve with simpler known functions.
Like polynomials or something?
Exactly, often polynomials. They're linear combinations of independent functions, each with an unknown multiplier or coefficient. These multipliers are then determined by invoking that stationary condition, taking the partial derivative of a with respect to each multiplier and setting it to 0. This process directly leads to a set of simultaneous algebraic equations, and importantly, it results in a symmetric coefficient matrix, which again takes that familiar form, KU-IL-R.
Okay, and you mentioned a key aspect about boundary conditions.
Yes. Critically, for the Ritz method, these trial functions only need to satisfy the essential boundary conditions. Those are the prescribed displacements. They don't necessarily have to satisfy the force conditions at the boundary beforehand.
And how does that compare to, say, the Galerkin method you mentioned? Is it similar?
It's related, but different in its philosophy. The Ritz method, by working with that energy functional ACL, naturally leads to symmetric K matrices, which is computationally very efficient. Contrast that with weighted residual methods like Galerkin. Galerkin also uses trial functions, but it focuses on minimizing the error in satisfying the governing differential equations directly. It tries to make a weighted average of the residual, the error vanish over the element. A technical detail is that in the pure Galerkin method, these trial functions generally must satisfy all boundary conditions, both essential and natural force. This can sometimes make setting it up a bit more complex, but it's incredibly versatile. It actually forms the foundation for many modern FEM formulations.
That's a fascinating distinction. The source mentioned an example with a non-uniform bar that really highlights this, didn't it?
Yes, that example of a non-uniform bar is great. It shows how the Ritz analysis can approximate the exact solution for displacements and stresses quite well. But what's really cool, and maybe a bit subtle, is this. If your chosen mathematical guesses, those trial functions, happen to have discontinuous derivatives, like sharp kinks or changes in slope at specific points, then those specific points effectively define the boundaries between your finite elements. It's almost as if the mathematics itself is partitioning the continuous bar into discrete pieces for you. It is a finite element analysis, emerging naturally from the choice of functions.
Wow, okay. And it's amazing how adaptable FEM is. You mentioned classifying engineering problems of truss, plane stress, plane strain.
Axisymmetric, beam, plate, shell conditions. Yeah. Each of these idealizations simplifies the physics in a specific way. and each has its own specific set of displacement, strain, and stress variables that you track. This allows engineers to choose the right kind of element for the job, making the analysis more efficient and relevant.
And taking that adaptability even further, isoperimetric elements, that sounds important.
Oh, definitely. Isoperimetric elements represent a more general and incredibly powerful approach. The real genius here, the key idea, is that both the geometry of the element, its physical shape, the XYZ coordinates, and its displacements, how it moves, the U, V, W, are interpolated using the exact same set of functions. These are called shape functions.
So the function describing the shape is the same type as the function describing how it deforms.
Precisely. This simple-sounding idea was revolutionary because it allowed engineers to easily create elements with curved boundaries. Think about modeling an airplane fuselage, or the smooth curves of a car body, or complex biological shapes. Isoperimetric elements let you map these complex curved geometries accurately using the same mathematical framework you use to figure out how they bend and stretch under load. It also allows for elements with a variable number of nodes, adding even more flexibility.
Okay, this is starting to sound like a monumental task, though. Breaking things down into potentially millions of elements, calculating all these matrices, solving all these equations. How do computers even begin to handle such a massive computational effort efficiently?
You're right. It is a massive computational effort. And efficiency is absolutely key. The implementation of FEM in computer programs like the SAP or ADNA codes mentioned earlier generally involves three core phases. First, there's the calculation of structure matrices. The program reads all the nodal coordinates and how the elements are connected. Then it computes the individual element matrices, stiffness, maybe mass and damping if it's dynamic, and crucially, assembles them into the big global structure matrices for the entire system.
Putting all the Lego bricks together, basically.
Kind of, yeah, but in a very systematic matrix-based way. Second, with that global framework in place, the program moves to the solution of the equilibrium equations, that KU equis, finding the unknown displacements, U. And finally, once the displacements are known, the third phase involves the evaluation of element stresses, using the calculated displacements and the element properties.
Thinking about storage and efficiency, you mentioned assembling these huge global matrices. The source talked about effective nodal point numbering. That sounds really important. I mean, if you number your nodes or elements badly, couldn't that make the matrix really messy and hard to solve?
Absolutely critical. Bad numbering can significantly increase what's called the bandwidth or the profile of the global stiffness matrix. Think of the matrix K. It's often sparse, mostly zeros, but the non-zero entries tend to cluster around the main diagonal. If you number nodes randomly, those non-zeros can spread out really far, making the matrix much larger in terms of storage and much, much slower to solve.
So smart numbering keeps the non-zeros tightly packed.
Exactly. That's why techniques like bandwidth optimization or profile minimization algorithms are built into FEM software. And related to that is how you store the matrix. You don't store all the zeros. A common efficient method is the skyline storage scheme, sometimes called a variable bandwidth or profile scheme. It only stores the elements within the skyline of the matrix, drastically reducing memory needs.
Okay, that makes sense for storage. What about the actual calculations within each element? The source mentioned numerical integration. How does that fit in?
Right. Evaluating those element matrices, especially the stiffness matrix, K equals EB, CBD, dV, often involves complex integrals over the element's volume or area. For anything other than the simplest elements, these integrals usually can't be solved analytically, with a simple formula. So we use numerical integration techniques.
Like methods you learn in calculus, Simpson's rule, things like that.
Similar ideas, yes. Methods like Newton codes, which include Simpson's rule, exist. But in FEM, Gauss integration, or Gauss-Legendre quadrature, is very often preferred. The reason is efficiency. For the same number of sampling points within the element, Gauss integration lets you exactly integrate a polynomial of a much higher order compared to Newton codes. It's generally more accurate for the computational effort involved.
I was really struck by a point in the source about this, though. It mentioned that sometimes if the order of integration isn't high enough, you can get these spurious zero energy modes. And it gave an example where a slight change, like from 2x2 to 3x3 Gauss points, completely changed the result from absurd to correct. Could you explain what those modes are and why they're such a danger?
Yes, that's a critical and sometimes subtle aspect of FEM modeling. It's called reduced integration. Sometimes you intentionally use a lower order of integration than needed to integrate the stiffness matrix exactly. This can actually be beneficial for certain element types, making them less stiff and perform better, particularly in bending. However, if you reduce the integration order too much, you can introduce these spurious zero-energy modes. Think of them as ways the element can deform without storing any strain energy. Phantom wiggles, essentially.
Phantom wiggles. That doesn't sound good.
Not at all. If your element has these modes, the global stiffness matrix might become singular or nearly singular. The analysis might fail, or worse, it might give you results that look plausible but are completely wrong because the element isn't resisting certain types of deformation properly. That example you mentioned where maybe a 2x2 gas integration on an 8-node plane stress element gives garbage results while 3x3 works fine perfectly illustrates this danger. The lower integration wasn't sufficient to control all the possible deformation modes of that element.
So if I'm understanding this right, the choice of element type or even the details of how you calculate its properties, like the integration order, isn't just about getting a slightly more accurate number. It can fundamentally change whether the results are even physically meaningful. That seems like a major responsibility for the engineer running the analysis.
It absolutely is.
Yeah.
You can't just treat FEM software as a black box. And related to interpreting results, it's important to remember that while displacements are usually continuous across element boundaries, that's how we assemble the model, the calculated stresses are generally not.
Wait, the stresses jump as you cross from one element to the next.
Often, yes, because stresses are usually calculated from the derivatives of the displacement field, and the assumed displacement fields might only match up in value, not in slope, across element boundaries. So you'll often see stress contour plots that look jagged or discontinuous. Engineers need to understand this. They often look at stresses at specific points, like the integration points, which tend to be more accurate, or they use averaging techniques to smooth the results for design purposes, but they need to be aware of the underlying discontinuities.
Given all these intricacies, element choice, integration, stress interpretation, what does an engineer really need to keep in mind when using FEM for a real-world design problem?
Well, effective modeling really requires a dual understanding. It's not just about knowing how to use the software. You need, first, a good qualitative knowledge of the expected physical response of the system. Have a feel for how it's likely to behave under load, what parts will be highly stressed, how will it likely deform. And second, you absolutely need a thorough understanding of the principles of mechanics and the specific FEM procedures being employed, the assumptions behind the elements you choose, the limitations of the analysis type. The source material, for instance, generally recommends using parabolic elements, like quadrilaterals with mid-side nodes, or ensuring elements aren't overly distorted, as these practices typically provide a good balance of accuracy and computational efficiency for many common problems.
Okay, so let's say we've built our model carefully, we've calculated our element matrices, assembled the global K matrix. Now it's time to actually solve KU equals R. What are the big ideas here for getting those displacements U, especially for static problems first?
Right, for static analysis, where things aren't changing with time, we're solving KU equal R directly. The most widely used approaches are direct methods, which are essentially sophisticated variations of Gauss elimination tailored for these large, sparse, symmetric systems. Several specific techniques fall under this umbrella. There's static condensation. This is clever. You mathematically eliminate internal degrees of freedom within an element or a group of elements, keeping only the degrees of freedom on the boundary. This reduces the size of the final system you need to solve.
Kind of hiding the inside details.
Exactly. And substructuring is basically an extension of that idea. You break your large structure into big chunks or substructures. You apply static condensation to each substructure, essentially creating a much smaller super-element stiffness matrix that only involves the nodes connecting the substructures. Then you assemble and solve this much smaller system and finally go back to find the details inside each substructure. Great for very large problems or parallel processing.
Makes sense for huge models. Any other techniques?
There's also the frontal solution method. This one is interesting. It processes the elements one by one. As each element is processed, its contribution to the global stiffness matrix is added, and any nodes that are now fully assembled, meaning all elements connected to them have been processed, are eliminated immediately using Gauss elimination. It kind of sweeps a front across the mesh. And behind many of these solvers, especially those using skyline storage, is the LDLT factorization. The stiffness matrix K is decomposed into a lower triangular matrix L, a diagonal matrix D, and the transpose of L. Once you have this decomposition, solving KU equal R for different load vectors R becomes computationally very fast.
Okay, that covers static problems. Now, what about when time is a factor dynamic analysis? The world is rarely static, right? Buildings sway, machines vibrate.
Absolutely. For dynamic problems, the governing equation becomes more complex. It's typically written as mu plus q plus ku argues rt. You have the mass matrix m times acceleration u, the double dot means second derivative with respect to time, plus the damping matrix c times velocity e, plus the stiffness matrix k times displacement u, all equaling the time-varying load vector rt.
Okay, so inertia and damping forces are added in. How do you solve that equation over time?
There are two main families of methods. The first is direct integration. Here, you basically step through time, solving the equations at discrete time points and
You're
apart.
picking small time steps.
Exactly. And within direct integration, there are two popular flavors. First, the central difference method, CDM. This is an explicit method.
Explicit, what does that mean?
It means the solution at the next time step, say t plus 8, is calculated using only information already known from the current and previous time steps, t and t8. You don't need to solve a system of equations at each step. You can calculate the next displacements directly. The catch is that CDM is only conditionally stable. Your time step has to be smaller than a certain critical value, which depends on the highest natural frequency of your finite element mesh. If 8 is too large, the calculation blows up. Because of this need for small time steps, it's often used for problems involving very short durations or wave propagation phenomena like impact or crash simulations.
Okay, so explicit is fast per step, but needs tiny steps. What's the other direct integration technique?
That would be the Newmark method or variations like the Hilbert-Hughes-Taylor method. This is generally an implicit method.
Implicit, so the opposite of explicit.
Right. Implicit means that to find the solution at the next time step, t plus 8, you actually need to solve a system of equations that involves the unknowns at that future time step. So each time step involves solving something like kut plus 8 equals rt plus 8, where k and r depend on the method's parameters and previous solutions. The big advantage is that the Newmark method can be made unconditionally stable, depending on the choice of its parameters, often called I and day. This means you can use much larger time steps without the solution blowing up. So for many structural dynamics problems where you're interested in lower frequency responses over longer durations, implicit methods like Newmark are often preferred. Your choice of 8 is then governed by the accuracy you need, not just by stability limits.
Interesting trade-off. Explicit is simpler per step but needs small steps for stability. Implicit is more work per step but can use larger steps based on accuracy.
Exactly. But direct integration isn't the only way to tackle dynamic problems. There's another very powerful approach: mode superposition analysis.
Mode superposition. How does that work differently?
Well, the basic idea here is quite elegant. Instead of solving the full coupled system of equations, mu plus c plus kur, directly in terms of the physical displacement to you, you transform the problem. You express the motion of the structure as a combination, or superposition, of its natural vibration shapes its modes. Remember those eigenproblems we talked about earlier? They give you the natural frequencies and mode shapes of the system?
Okay, so you use those inherent vibration patterns.
Precisely. By using these mode shapes, you can transform the big coupled set of equations into a much smaller set of uncoupled independent equations, one for each mode you choose to include. It's like breaking down a complex dance into a combination of simpler fundamental moves. This transformation dramatically simplifies the problem, especially if the damping in the system has a special form called proportional damping, like Rayleigh damping, where C is a combination of M and K, C equals M plus C and GK. In that case, the modal equations become completely independent and very easy to solve.
That sounds much simpler, but how do engineers even find those mode shapes and frequencies in the first place, especially for a complex model with thousands of degrees of freedom?
Ah, yes, that raises an important question. Finding those natural frequencies and mode shapes involves solving that eigenproblem we touched on earlier. For structural dynamics, it's typically the generalized eigenproblem, CUF-FO, or sometimes written as CUS-FO, where FO.
So you need to solve this CUF-FO equation. Is that easy?
For small systems, maybe, but for real-world models, these are often large eigenproblems. We might be talking about systems with hundreds of thousands or even millions of degrees of freedom. That's the size n of the matrices K and M. And often you don't need all the possible modes, maybe just the lowest, say, 50 or 100 modes, that's M, because they usually dominate the structural response.
So finding just the important few out of potentially millions.
Exactly. And there are various sophisticated computational methods developed specifically for this. For finding just one or a few eigenpairs, there are vector iteration techniques, like inverse iteration or forward iteration. For finding eigenvalues in a certain range, there are polynomial iteration methods, like determinate search, or Sturm sequence methods for finding all eigenpairs usually only for smaller problems, there are transformation methods like the Jacobi method.
Wow, a whole zoo of methods. Which ones are used for those large problems typical in FEM?
For large eigenproblems where you need a significant number of the lowest modes, meter 60 and 500 as a rough guide, combinations of techniques are usually best. One very powerful and widely used technique is the subspace iteration method. It's essentially a block version of vector iteration. It simultaneously iterates with a subspace of vectors, say Q vectors, where Qm, to find the lowest m eigenvalues and corresponding eigenvectors efficiently. It leverages the good properties of vector iteration, but accelerates convergence significantly for multiple modes, often involving fewer expensive matrix factorizations.
Okay, so there are clever ways to extract just the essential dynamic characteristics even from massive models.
Definitely, these eigensolvers are critical components of modern FEM software packages.
We've certainly taken a deep dive into the finite element method today. We've gone from its foundational concepts, breaking continuous things into discrete bits, all the way to advanced applications and the pretty sophisticated computational techniques that actually make it all possible. We've seen how engineers idealize complex physical problems, break them down into these manageable pieces, these finite elements, and then leverage really powerful mathematical and computational tools to predict how structures and systems behave under various conditions.
And that ability, the ability to accurately model and analyze these complex systems while always understanding the underlying assumptions and limitations, that's crucial, is precisely what enables engineers to design structures that are not only cost-effective, but critically safe for public use. I mean, without FEM, many of the incredible structures and machines we rely on every single day simply wouldn't exist as they do, or they'd be much heavier, much more expensive, or potentially less safe.
So thinking back on everything we've discussed, what really stands out to you listening to this? Think about that fundamental idea, breaking down a complex, seemingly intractable, continuous problem into smaller, discrete, solvable parts. That core concept seems incredibly powerful, not just in engineering, but maybe in other areas of problem solving too.
That's a great point to ponder. Consider how this modular approach allows for the analysis of almost anything, from the stresses in a massive cooling tower, predicting where cracks might form, to the intricate dynamic response of a building during an earthquake, figuring out how it will sway and whether it will remain standing. It really raises an important question, doesn't it? In a world that seems to be generating increasingly complex systems, think about climate models, economic systems, social networks, biological processes, what other fields could potentially benefit from applying a similar finite element mindset? That fundamental idea of dissecting a massive continuous challenge into smaller, interconnected, perhaps more manageable, solvable parts, just like engineers learn to dissect a bridge or an airplane wing. What problems could that unlock?